Hello guys and welcome back to another video tutorial in the IB IGCSE chemistry series. In today's video tutorial, I'll be going over the single displacement reactions, which continues from our previous IGCSE IB chemistry video tutorials, which was based on the synthesis and decomposition reactions. So to get started, we're just going to be looking at single displacement reactions today, and in the next video tutorial, I'll be doing the double displacement reaction video series. So what is exactly single displacement reaction? Well, first, what we have to understand is that we have a reactivity series, and in our reactivity series, it shows which elements are more reactive than others, and as such, the most reactive elements tend to displace the least reactive elements. As usual, I have prepared this PowerPoint slide, and like I said, if you're interested in having these PowerPoint slides, please let me know in the comment section. I'll do my best to post it so that you can have access to it. So this PowerPoint slide is focused on single displacement reactions, and as usual, I have also included the periodic table and the polyatomic periodic table, and now I have included the reactivity series as well. So looking at the reactivity series, we can see on the right here, it says that the activity series or reactivity series is a ranking of the reactivity of elements or metals, in this case metals, relative to each other. The most reactive metals, as you can see in the reactivity series here on my left, I'm just going to zoom it in. You can see that the most reactive metals start with lithium and go all the way to gold, which is the least reactive metal. So basically, the elements that are on top of each other are more reactive than the elements or metals that precede them. And so we also have a reactivity series for halogens on the periodic table, and that includes, of course, fluorine, chlorine, bromine, and iodine. And you can see that it goes from the most reactive, which is fluorine, all the way to iodine, which is the least reactive. So therefore, this activity series is what we're going to be using as a reference chart to understand more how single displacement reaction occurs. Please take note that it is not just single displacement reaction that we do have. We also have double displacement reaction, and I'll be doing another video tutorial for that. So the most reactive metals, like I've mentioned, lithium and potassium are at the top of the activity series. The least reactive metals are usually at the bottom, as you can see this arrow going from top to bottom. And hydrogen is also included in the series, even though it is not a metal, but because it forms a positively charged ion like a metal, therefore it has been included. And anything that hydrogen is more reactive than basically would mean that there wouldn't be any reaction. So with metals such as copper, mercury, silver, platinum, and gold. So again, what it said here is because hydrogen is included in the series, like I said, it's not a metal, but it forms ions just like metals. And also including hydrogen makes it easier to predict which metals react in acids and in water. The activity series is based on two important generalization, guys. One of them is that one element can displace elements that is below it. So basically, the most reactive element would displace the least reactive element depending on the chemical reaction. And the farther apart the two elements are, that also tells you the more likely it is that the displacement of the reaction would occur quickly or not so quickly. So of course, if you have a metal that is much reactive, for example, lithium, and you have it reacting, for example, with I don't know, maybe silver nitrate, for example. So you can see the gap between lithium and silver is pretty large. So that would definitely show how fast the reaction would occur. Being that the gap is quite large, it would be really fast since lithium is most reactive. And of course, silver nitrate, which involves silver, is least reactive. To determine whether or not a reaction between an element and a compound will proceed, you have to look at the relative positions of the two metals in the activity series. So like I said, this is going to be a reference chart that you would need to come back to kind of look and see which metal displays which one. If the higher or more reactive metal is the element, then the reaction would proceed. Of course, if the metal that is more reactive is the first metal reacting with a non-reactive metal or least reactive metal, so it has to be the first in a chemical equation or in a chemical reaction. If the higher metal is in the compound, then of course no reaction would occur. So basically, guys, what they mean is, like I said, if you have the single metal, for example, lithium reacting with silver nitrate, definitely a reaction is going to occur because you have lithium first and it displaces silver and it produces lithium nitrate, for example, and then silver is displaced But in a situation where you have silver reacting with lithium nitrate, in that case, silver is occurring first, so it cannot displace lithium since silver is least reactive, and it's not having the capability to displace lithium, which is above it and most reactive. So in that sort of sense, that there would be no reaction. That's what they mean by no reaction would occur. So here it says predicting single displacement reactions. It says reactions involving a metal and an ionic compound using the activity series. It says write down a balanced chemical equation for the reaction that occurs. So if you guys can see, that's pretty much what it says in this black highlighted section. And then we move on, guys, to this part here. It says, so I'm going to try and zoom it out so you can see. So we are looking at the introduction to how single displacement reaction occurs. And like we mentioned, single displacement reaction is a reaction in which an element displaces another element in a compound, producing a new compound. So if you look on the left side, you would see, for example, a highly reactive element or metal could be A, and then we have a least reactive element or metal that is in a compound, which is BC, producing the displacement of A, which is displacing B, so that A reacts or combines with C, and then B is displaced. So it pretty much symbolizes that form of how a displacement reaction occurs. So the reaction of nickel with an acid follows the same pattern. So this is an example as other similar reactions. These reactions are considered as single displacements, and in a single displacement reaction, one element displaces or replaces an element in a compound. And like I said, it's basically following this pattern where we have element A reacting with the compound BC, where element A is displacing B, perhaps because element A is at the top of the reactivity series or activity series, and element B that is with the compound is at the bottom. So therefore, element A can displace element B, and so element A reacts with C and then displaces the element B. So we're going to see this in a real life example or in a realistic example. It further goes on to say single displacement reactions are useful when you need to recover a dissolved metal from solution. For example, copper 2 sulfate is a common chemical used in high school labs. Each year, schools generate a considerable volume of copper 2 sulfate. Unfortunately, dissolved copper ions are toxic, and so they must be treated before disposal. And this is why one way to treat such a reactive or toxic, rather than reactive, toxic metal is by adding a piece of reactive metal like zinc before displacing or disposal. So a single displacement reaction would occur in which zinc is going to displace copper from the solution. So if you guys look at this solution, we have zinc, which is a solid, we have copper sulfate, which is aqueous, and we see that when we look at the reactants and we look at the products, we see that the product form is zinc sulfate. The reason is because zinc is displacing copper. And how does that happen? Well, if you go back to the reactivity series, guys, you can see that zinc is way above copper. So zinc is right here and copper is right here. So because zinc is above copper in the reactivity series, it can displace it in an aqueous solution, which is what we have here, or in a compound. So this is why zinc displaces copper, so it can combine and become zinc sulfate, which is an aqueous solution, and then copper solid metal. Zinc can also react with solutions of many other metal compounds, and so in other words, we could say zinc is a reactive metal. Gold, on the other hand, if you look at the reactivity series, you can see that gold is kind of on the least reactive sort of metal. Now we're going to look at some examples of how single displacement reactions are predicted. Once you're given a question, they usually would give you a chemical reaction, and they would say a chemical equation, and they would ask you to determine whether a single or double displacement had occurred. For a single displacement reaction, we have to consider the fact when this reaction involves a metal and an ionic compound. So using the activity series, what you need to do, of course, if they don't already give you the chemical equation and they give you some sort of scenario where an experiment had occurred and you have to derive the chemical equation, then you must always refer back to the activity series, like I said before. So using the activity series, you need to write a balanced chemical equation for the reaction that occurs. So this is a question, this is a sample problem 1, as you can read here. And it says that you need to write a balanced chemical equation for the reaction that occurs when magnesium metal is placed in a solution of copper 2 sulfate. If you predict that no reaction would occur, then you should write no reaction. Step 1 says you need to first write the chemical formulas of the reactants and, of course, identify the elements and the compound. So what we can derive from this problem 1 is that it says that a reaction had occurred between magnesium and copper 2 sulfate. So we know that magnesium and copper 2 sulfate are the reactants. Obviously, to determine what the products are going to be, that is where we need to use the displacement, the activity series, to decide what is going to displace what. If magnesium can displace copper, so it forms magnesium sulfate and copper. If not, then there would be no reaction, as it says on the problem. So we follow the same pattern of how the single displacement reaction would work, where element A is reacting with BC compound and element A is displacing B, which is, combining with C, and B is being displaced. So in this case, the element is magnesium and copper sulfate is the compound. And when we, react them together or combine them using their ionic charges, that's another thing to determine the right chemical formula, because you are given just a scenario. And if you guys remember, in our first video tutorial, we learned how to determine chemical formulas by writing the ionic charges of the elements and compounds and then kind of, switching them together or simplifying them. In this case, magnesium has an ionic charge of +2 and sulfate has an ionic charge of -2. If we simplify these two, this element magnesium and polyatomic ion sulfate, we can see that the two cancel out, and so the formula would be MgSO4. So this would ideally be the formula that would produce the product. But the thing is, how did we actually get to this formula? Why did we say that this is what the product would be? Well, when magnesium reacts with copper sulfate, if you go back to the activity series, you need to check the position of magnesium and copper and decide which one is going to displace which one. As you guys can see in the reactivity series, magnesium is way above copper. So magnesium is here and then copper is here. So which means magnesium can successfully displace copper from the copper 2 sulfate aqueous solution, and it will form the magnesium sulfate, which is why we need to determine the right chemical formula. And of course, it will displace copper. So this is what we have here, guys, in our step 4. So magnesium displaces copper and then combines with sulfate, so it forms magnesium sulfate, of course, following the rules of how to get the right chemical formula, as in step 3, it is MgSO4, and then copper as a solid is displaced. Another example of a scenario where you could have single displacement reactions are with reactions that involve a metal and an ionic compound. So here it says, using the activity series, you have to again write a balanced chemical equation for the reaction that occurs when lead, in this case, is placed in a nitrate solution. If you predict that no reaction would occur, then please write down no reaction. So lead is reacting again or is placed in a zinc nitrate solution. So there should be some sort of displacement. So just to continue, I'm just trying to find where the continuation goes from here. So I haven't included that part of the chemical reaction of lead being displaced in a zinc nitrate solution, which of course is ZnO3. But again, if you go up to the activity series, you should be able to determine which one is going to displace. If lead is reacting with zinc nitrate, so you need to see that lead actually comes under zinc. So therefore, there would be no reaction since lead is under zinc. It doesn't say zinc reacting with lead nitrate, the opposite. So remember, lead is reacting with zinc, but lead is actually placed in a zinc nitrate. Unless if it's, as they say, zinc nitrate, lead is placed in zinc nitrate, then in that situation where zinc can displace lead, because it is above it in the activity series. However, if we go down, there are a couple of questions here that says we should practice. We're going to practice some questions. I just wanted to see, for example, here was with lithium and with sulfate. So it was lithium with hydrosulfate. Sulfate acid, sorry, not hydrosulfate. So lithium with sulfate acid. And so lithium, of course, because it's reacting with hydrogen. Okay, so this is continuing from here. So we're going to look at this part. So we've looked at the part here where we've seen when a reaction involves a metal and an ionic compound. And guys, it's the same thing. Sample problem 1 is actually the same as sample problem 2, which is the reason why I did not put the reaction here, because it was similar to what was in sample problem 2. As you guys can see, it was saying in sample problem 1, it says magnesium metal is placed in a solution, which is the same thing as you're saying zinc is placed in a zinc nitrate solution. So it's the same thing. You're going to have lead is placed, in a zinc nitrate solution. So you're going to have lead on this side where magnesium is reacting with zinc nitrate. And of course, no reaction would occur in that situation, which is what I was saying depends on what is displacing what. Because the reason is if lead is placed in zinc nitrate, but lead is below zinc. So zinc is above lead. And so zinc is more reactive than lead. And so lead cannot displace zinc. All right, so guys, we're moving on to this part of this note slides before we do some practice. And we're now looking at how we can do single displacement reactions when these reactions involve metals and water or acids. And then it says not all single displacement reactions involve a metal in an aqueous solution of an ionic compound. Sometimes the reactants are a metal and a compound that contains hydrogen. Amongst the most familiar hydrogen compounds are water and acids. The same procedure outlined above can be used to predict displacement reactions involving acids and water. These tips will help. Now, they said whenever you are reacting metals with water or acids, you need to treat the acids as if they were ionic compounds. For example, hydrochloric acid, hydrogen has a positive charge, chlorine has a negative charge, sulfate acid, hydrogen has a positive charge again, and sulfate has a -2 charge. So you treat them as if they were ionic compounds, and the same thing happens for water. You treat it as an ionic compound, which means hydrogen and hydroxide. Now, in a reaction that involves a metal and an acid, for example, in this question here, it says use the activity series to write a balanced chemical equation for the reaction that occurs with when lithium is added to sulfuric acid. So guys, sorry I was saying sulfate. I was trying to figure out what was the name of this acid. It just slipped my mind. So it's sulfuric acid, H2SO4. So when lithium is added to sulfuric acid, what actually happens? Since we're supposed to treat the water and acids just as ionic compounds, if we have lithium as a solid reacting with the acid, or in this case, this aqueous acidic solution, then we are going to treat this solution as, individual ionic compounds, like individual ionic charges. So lithium is a solid. We follow the same pattern of single displacement reaction. However, if we break down this compound into individual ionic charges, then hydrogen would have a plus charge and sulfate would have a 2- charge. Once we've done that, the second step you need to do when you're doing a single displacement reaction involving a metal and an acid is to identify again which one of them is higher on the reactivity or activity series. So the element or hydrogen, because you've now but you've now broken down this compound into their own individual ionic charges, then you now have hydrogen present. So you now need to know which one of them is going to display which one. So again, if the element that you are reacting with hydrogen is higher, then a reaction would proceed. However, if hydrogen is higher, and how do you know if hydrogen is higher? It's normally going to be on the side on the left. But because lithium is on the left, so it means it's the one that is reacting with this acidic solution. So now you just have to check and see on the activity series if lithium is above hydrogen. So if hydrogen would be above lithium, then it doesn't really matter where the positions are. You just really have to check where this element reacting with hydrogen is on the activity series. So if hydrogen happens to be above the element, then no reaction would occur. So if we go back to the activity series again one more time just to double check together, we would see that hydrogen is here with these asterisks, and then of course we have lithium, which is way above it. So lithium is above hydrogen, which means a reaction would occur. So hydrogen is not above lithium. So if we go down again, it means that lithium can now displace hydrogen. And so if we look at the next part of this equation, we're going to see that lithium displaces hydrogen. After the third step, of course, would be to determine the right chemical formula of the compound that is going to be formed, because you've seen on the activity series that lithium is going to displace hydrogen and combine with sulfuric acid. So once you've seen that, you now need to derive what the chemical formula is going to be for the product. Again, that will be based on the strategies that we've used before to derive chemical formulas. We have to write out their ionic charges. So the ionic charge of lithium is +1 and sulfuric acid is 2-. So we crisscross that, which means that this 2- or this 2 charge goes to lithium. So it's Li2, and this +1 goes to SO4. By convention, we don't need to write it. So it's Li2SO4. And then, of course, the step 4 would be to write a balanced equation. Now that we know what the product's going to be, lithium is reacting again with sulfuric acid. Lithium displaces hydrogen and then combines with sulfuric acid, as we can see on the product side, to form lithium sulfate. And then, of course, hydrogen gas is released. And then the last sample problem is, again, involving reactions that involve metal and water. So here it says that you're going to use the activity series to write a balanced chemical equation for the reaction that occurs when sodium is added to water. If you predict, again, that no reaction would occur, then you'd write no reaction. So what we need to know about the reactions that involve metal and water is that first we need to write down the chemical formulas of the reactants, and underneath we need to determine the atoms and the ions that are involved. So we know that sodium is added to water, so sodium has a chemical formula of Na. And water, of course, H2O. We know whenever we have reactions that involve water or acids, we need to split them into their ionic compounds. So that's pretty much what we're doing. And now we need to use the pattern of single displacement reaction, which is A reacting with B, C compound, and A displaces B to combine with C. And so in this case, we need to look, now that we've broken down water compound into its respective ionic charges, we need to see if sodium is higher or lower than hydrogen on the periodic table. On the activity series, sorry guys. So identifying which one is higher, which element is higher on the activity series would definitely know or determine how the reaction is going to proceed. Of course, like we said before, if hydrogen happens to be higher than the metal or element that is reacting with it, then no reaction would occur. In this case, because sodium is higher than hydrogen, therefore a displacement would occur. So that means that sodium would combine with hydroxide, and then we would get sodium hydroxide. And step 3, this is where we determine the chemical formula. And of course, hydrogen gas will be displaced. And so this is what we have here in step 4. And I forgot to mention, guys, it is always important after a single displacement reaction that you actually balance the chemical equation. Okay, guys, so what's next? If you're wondering what is by the side here, it's just more examples and figure diagrams of this reaction that we just looked at right now. And so we're moving into our slide 8 before we do some examples. And now we're looking at what about reactions that involve halogens. So the halogen family, as you guys may or may have not noticed, if you look at the activity series, you see that the halogens also have their own activity series, starting with the most reactive halogen, which is fluorine, all the way to the least reactive, which is iodine. So they do have their own reactivity series. So we also have to follow that when we're looking at halogens. So the elements of the halogen family also have their own activity series, like I said, based on the displacement reactions. For example, figure 7 shows the reaction that occurs when chlorine gas is bubbled into a colorless solution of potassium iodide. The reddish color indicates that the elemental iodine was produced in the solution, and the chemical equation for this reaction would be this. So if chlorine gas was bubbled into potassium iodide, that would mean we would light chlorine with the chemical formula of Cl2 plus Ki, which is potassium iodide, before we even put the two molecules in front, because that is only when we balance the chemical equation. So now once we have our chlorine and our potassium iodide, of course, the normal thing would be to go check your displacement activity series, and you can see that chlorine is above iodide. So chlorine is more reactive than iodine. So which means chlorine is going to be displacing iodine, which is really what's happening here. So if chlorine is displacing iodine, it means chlorine is going to combine with potassium, and so we get the formula of KCl. Of course, guys, don't forget how we derive this formula. Remember that K, which is potassium, has a plus charge or plus one charge, you could say, or just plus, and chlorine has a minus, so these charges minus one, so they cancel out. So this is why the chemical formula is KCl, if you're wondering, which is what we have here. And of course, the iodine or iodine aqueous is being displaced because chlorine is more reactive than it. So it says, note that the single displacement pattern for halogens is slightly different from the patterns of metal. This is because a negative anion is being displaced rather than the positive one, as we've seen with metals. So now we're going to scroll to the last part here. And here it just basically shows us the reaction. It says, for example, if bromine reacts with potassium iodide in this solution, so in this case, the balanced equation would be Br2, bromine's chemical formula, again with Ki. And then if you go on the displacement activity series, you guys can see that bromine is actually, again, above iodine. So right above it, so that means it can successfully displace it. So it combines with potassium and it becomes potassium bromide. And so this is what we have, KBr. And again, we get this chemical formula based on the ionic charges of potassium and bromine. And then, of course, iodine or iodide is being displaced as an aqueous solution. But if you guys look here, in this case where we actually have iodide or iodine reacting with, so you can see that this reacts with, according to this, with potassium chloride, then in this case there is no reaction. And the reason why there is no reaction is, if you go back to the activity series, guys, iodine is the least reactive element of the halogen family. So it cannot displace potassium at all. So there is no reaction occurring. So that's one thing. Another thing would be, so I'm going to scroll back down so that we can look at it. Okay, we're here, guys. So there is no reaction. So that says, because you would expect iodine to be below with, oh no, that's for bromine. So they said the evidence from similar investigations is the basis for the activity series. Just like the activity series of metals, it also helps us to predict which elements will displace others from compounds. And fluorine, for example, displaces all of the halogens because it's the most reactive. So like I said, guys, this is not going to produce anything because obviously iodine is the least reactive, so it is below bromine, so it's the least reactive, so it cannot displace potassium. It cannot displace chlorine. Sorry, guys, I was saying potassium. Sorry about that, chlorine, because we're looking at the halogen family. So it cannot displace chlorine, so there is no reaction. So it doesn't displace it so that it produces potassium. The last one is, what about single displacement reactions that involve solids? So this one is a little bit different. Again, we have to look at the activity series to determine what displaces what. But here it says some industrial single displacement reactions involve only solid reactants. For example, if you're making iron for steel, so they're just giving you the situations of where you might have single displacement reaction of solids. And they say, for example, when you're making iron for steel involving reacting iron with this which involves reacting iron ore, guys, that is Fe2O3, with coke, which is carbon, in a blast furnace at 1000 degrees Celsius. So this is much, much hot enough so you can melt the iron to form steel. And so this is the chemical reaction. And again, it goes by the activity series as well. So you can see that, of course, iron is being displaced. And then, of course, you can see that carbon combines with oxygen. And so you get carbon oxide and iron, which is being displaced. So everything is really, for single displacement or double displacement reactions, you always have to look at the reactivity or activity series, guys. It's very important so that you can determine what exactly is supposed to be displaced. All right, guys, we're going to be looking at the last part of our series today, video tutorial series, which is this part. We're going to do some single displacement reactions. So I'm just opening this on Google Slides so that we can do some of it. and you can try to do the remaining as practice for you later on. So I'm just going to do perhaps the first 3 or the first 5. So I'll copy this and I'll put it on our Jamboard as usual. I just hope it can copy though. I hope it does. Okay, guys, I'm just going to have to, if you don't mind, it's the same thing that happens last time. I'm going to have to make it bigger, and then I'll just take a screenshot so we can just do it on the Jamboard. Okay, there. So let's start off with the first part of this single displacement equation reaction question. So the first question says that we are reacting silver with potassium nitrate, and we need to determine what will be the right of course product based on the activity series and using single displacement reaction. And remember, single displacement reaction is when one element displaces another. So if we go back, what we're going to need from here is to be on our activity series, because we're going to use it as a reference chart. So I'm just going to stay on this part, and then we will use this. So according to our activity series, we see that the most reactive, of course, starts with lithium. And according to this chemical equation, we can see that we are trying to displace, we want to see if silver can displace potassium, because this is a metal to metal single displacement reaction. So we see that silver is actually here where you see my mouse moving, and potassium is actually here. So there is not going to be any reaction because silver cannot displace potassium, rather potassium displaces silver. So this means there is no reaction, NR. Now let's look at the second question. In the second question, we have zinc reacting with silver nitrate. And so if we go back to the activity series, we check for where zinc is, since it's the first one that occurs in this chemical reaction or chemical equation, and we look for where silver is. So if we go back, we can see that zinc is here and silver is under zinc, which means that there is a reaction going to occur where zinc can displace silver since it is above it. So if zinc displaces silver, it means that we are going to form the chemical compound of ZnNO3, that is zinc nitrate 2. So guys, if you're wondering how I'm getting all of this chemical formula, please go and watch the first video tutorial where we learned how to be able to how to be able to create chemical formulas or derive them. So zinc is going to displace silver and it's going to form zinc nitrate, and of course silver is going to be displaced. Now, the third question is where we have aluminum reacting with sulfuric acid. So this is where we have a metal like we saw reacting with an acid. So here we would have to, of course, displace, you would have to break this compound into its ionic form, ionic charges. So it will be something like this, where you have hydrogen, since there are 2 atoms, so it means hydrogen plus, and then of course sulfuric acid, which has, it's a polyatomic ion with a charge of -2 or 2- as you wanted to write it, however. So then you have to determine if aluminum is above hydrogen and so it can displace it, or if it's the other way around. So we look at aluminum and we find that aluminum is right here where you see my mouse moving, and we find hydrogen is below. So indeed a reaction is going to occur where aluminum is going to displace hydrogen. So that means that it will form aluminum sulfate. So that would be Al2, guys, SO4 3. Okay, SO4 3. I'm going to put it down here. I hope you guys can see. SO4 3, and that's going to be reacting with displacing, of course, hydrogen gas, so H2. And I forgot to talk about the balancing of chemical equations. Please make sure it's balanced. So for this number 2, I forgot to put 2 here, since we have 1 atom of zinc here, 1 atom of zinc. And then, of course, we have... so we look at silver, we have 1 atom of silver, 1 atom of silver, and then we have 2 atoms of nitrate here, and we have just 1 atom. So that means we have to put a 2 in front, of course, so that it is balanced, right? So we have to put a 2 here, guys. So a 2 has to go here, so it's balanced. So we have 6. If you times 3 times 2, we have 6 atoms here, and we have 6. But then silver now is 2, so we also have to put a 2 here so we can get a balanced equation. So please take note of balancing your chemical equations. And then for aluminum reacting with sulfuric acid, like I said, aluminum displaces the hydrogen since it's above it in the activity series, and it forms aluminum sulfate, which is La2SO43. Remember, we get this formulas because of their ionic charges. So La means aluminum is a +3 or 3 plus. And then sulfate, of course, it's a polyatomic ion, which has a charge of 2 minus. When we crisscross the charges, then we see that, of course, aluminum gains this 2 and sulfate gains the 3. And hydrogen gas is released, so H2. So I'm just going to try to see if I can, I want to erase this so I can just write the right chemical compound. So it's H2SO4. I just broke that down for you to see. And so this produces this aluminum sulfate. Now we have to check and see if this equation is balanced. So we have La2SO43. We have hydrogen here, which is 2. But if you look here, we have 2 atoms of aluminum and we have only 1 here. So that means we have to put 2 behind here. And so we have 2 atoms of aluminum here. We have 2 atoms of aluminum. And what else do we need to balance? Oh, okay. We also have sulfuric acid. It's 3 atoms, but here it's just 1. So obviously that means we can only put 3 here. So it's balanced. So it's 3 atoms of sulfuric acid, but now hydrogen has 6. So that means we also have to put 3 here. And so this is now a balanced chemical equation. Okay, guys, so the fourth question is we are reacting chlorine with potassium iodide, and I think we saw a reaction, I think the exact same reaction in our slides, if I'm not mistaken, when we were looking at halogens. Yes, we already have seen it, so we're not going to do that. Just to zoom it in for you guys, it's actually this one. So we saw that chlorine reacts with potassium iodide, and we saw, of course, since chlorine is above iodine on the activity series, it's going to be displacing it. So you're going to have this, in the end, you're going to have this final equation, which is balanced. So chlorine displaces iodide or iodine, and it, forms or combines with potassium. So we get potassium chloride and iodine, which is being displaced. So eventually you're going to have this kind of chemical equation, which is balanced. So we're not going to do this one. This one is lithium reacting with water. So obviously, if you look again, remember when we are reacting metals with water or acids, again, you have to break down that water into its ionic charges. So that would mean it's plus hydrogen plus, since there are 2 atoms of water, and then hydrogen plus again, and then of course oxygen 2 minus. So again, this is pretty much how you're going to break it down. So now, once you've broken it down, you have to check the activity series and see which one displaces which. Of course, lithium is much higher than hydrogen. It's way at the top, the most reactive. Hydrogen is way at the bottom. So lithium is going to displace hydrogen, and of course, that's going to mean that it's going to be forming lithium oxide and hydrogen gas to be displaced. So lithium oxide, LiOH. And then, of course, hydrogen gas. So now we need to balance this equation. So I'm going to erase this part and just write it as normal water, the chemical formula, which is H2O. And now we're going to try and balance the equation. So if we look here, let's see what we need to do. So lithium on this side is lithium 1,1, and then lithium hydroxide. We have 3 hydrogens on the product side, 1 and then plus 2, which is 3. So that's definitely not balanced. And here we have 2. So we need something to make it even. So which means we can put 2 here behind lithium hydroxide. And so now we have 2 atoms of hydrogen on this plus 2, which is 4 on this side. And then we have 2 lithium atoms and so 2 oxygen atoms. So which means we need to balance that. So if we put 2 here, in front of water on the reactant side, that's going to balance both the hydrogen, which now becomes 4, and also the oxygen, which now becomes 2, just as here. And so lithium, all we have to do is just put 2, so it's a balanced equation. And that's it, guys. So this is where we are going to stop our video tutorial for chemistry on single displacement reactions. I hope this video was useful for you. If you have any questions, let me know. I'm planning on doing more video tutorials every weekend, like I said, and you can try to practice doing from question 6 to 10. All right, guys, I hope you have a great day, and I'll see you in our next video tutorial.